Well, here we go with lesson 14, section 6.7. It's going to wrap up section 6.7, applied trigonometric problems. So we're going to have two types of problems in this lesson. We're going to have navigation problems, or navigation and surveying problems, and then we'll also have directional problems with airlines. There'll be the compass headings type problems. But let's start with bearing problems first, navigation or surveying problems. And our point P will always be our point of origin here, and you can see we've got point Q out here, and we want the bearing from P to Q. So we want this angle right here, and we want to know what the angle that PQ makes with the north-south line. So we always talk about north or south first, and we have an acute angle, and we talk east or west next. So this one's going to be north theta degrees to the east. We always start with north or south, excuse me. We always have an acute angle, and we always finish with east-west. We would never say east-north. We always say northeast or northwest, southeast or southwest. So here's we're going to do 4 examples here for you, and we want the bearing from point P to point A, and you can notice there's a 30-degree angle here between the north line and vector A, and so that's the angle we want. And so we'd say that the bearing from point P to point A is north 30 degrees to the east. Let's do it the one down here. Now here we want the angle from the south line over to vector B. And you notice we only gave you the 15-degree angle between the east line, due east, and bearing B, the vector B. And so we had to subtract that from 90. And so we'd say south 75 degrees to the east. Now this one's a little easy because we gave you the 20-degree angle between the south line and the vector ending at point C. And so we'd say the bearing from P to C is south 20 degrees to the west. And last one. Again, we gave you the angle between the west line and the vector containing point D. So if we want the bearing from point P to point D, we go north, and we had to subtract 35 degrees from 90 and got 55 degrees. So we'd say north 55 degrees west. So look at these. They all have north or south first. They all have an acute angle, and they all have east or west last. And here, recap it again. North or south first, east or west is last, and the angle in the middle is always acute. Before we go into the application problems, let's hark back to your geometry days. And you can probably remember when you had 2 parallel lines cut by a transversal. We had 2 things we were interested in: alternate interior angles and same side interior angles. Well, first, alpha 1 and beta 1, and therefore beta 2 and alpha 2, these are supplementary angles because these are 2 angles that make up a straight line. So these 2 have to be supplementary, and these 2 have to be supplementary. Supplementary, remember, add up to 180. We would say that beta 1 and beta 2 are equal to each other because they are alternate interior angles of 2 parallel lines cut by a transversal. For the same reason, alpha 1 and alpha 2 are congruent to each other, or equal to each other, because they are alternate interior angles of 2 parallel lines cut by a transversal. Let's talk about same side interiors. Alpha 1 and beta 2 are supplementary because they are same side interior. They're the same side of the transversal. Beta 1 and alpha 2 are also supplementary because they are same side interior angles. So we have same side interiors are supplementary, alternate interiors are congruent, and we're going to use that in our examples today. And this is the part of geometry people normally didn't hate. I think you hated all the rest of it, but you didn't hate this. So here's our first problem. A ship leaves port and sails in the direction of north 78 degrees west at a rate of 35 miles an hour. At the same time, another ship leaves the same port and travels south 12 degrees west at a rate of 21 miles an hour. How far apart will the 2 ships be after 3 hours? So the first thing I do is I draw a north, south, east, west. And I lay in the bearings. And so you notice the first ship was going faster than the second ship. So I made that bearing longer. You'll do yourself some favors. And you don't have to pull out a protractor and a compass and a ruler and get these perfect, but try to figure out about 78 degrees and try to get about 12 degrees down here. And so the first ship was north 78 to the west. The second ship was south 12 degrees to the west. And so I kind of put those in there. And again, I made that first line longer than the second line because I was kind of looking ahead here. And so that makes a triangle. And we want to know how far apart the two ships are after 3 hours. Well, our old favorite equation is distance equals rate times time. And so the distance the first ship travels is the rate, 35 miles an hour, times the time. So it traveled 105 miles. And the second ship was also on the sea for 3 hours, but it was only going 21 miles an hour. So 21 miles an hour times 3 hours is 63 miles. And that 63 is about, well, not half, but 2/3 there of the 105 miles. And again, my lines represent that roughly. Something else that's interesting is right here at the bend is a right angle. If it's 78 degrees from north to that first line and 12 degrees from the south to the second line, if you add those up, you get 90 degrees. And from due north to due south is 180, leaving only 90 degrees in here. And I will tell you, for all of our problems, since we're dealing with right triangle trigonometry, the right angle will be right there at the port between the two vectors. So we do have a right triangle. That's a good thing. So if we have the right triangle and we have the two legs, then we'll use Pythagorean theorem to find x. And here, ooh, that jumped out, didn't it? And we have x squared equals 105 squared plus 63 squared, and it works out to 122.4 miles. So now that answers part A. How far apart are the ships after 3 hours? 122 miles. Part B seems to be the part that gives most people headaches. What's the bearing from the first ship to the second ship? So now we've got to get from the first ship to the second ship. You notice I changed that to red line there. That's what we want. We want the bearing from the first ship to the second ship. So I put a north, south, east, west, and normally I don't mark the initials because I don't want to clutter up my drawing. And this is where it gets a little complicated here. But I want to get from the first ship all the way down here to the second ship. And so I need a bearing, and it looks to me like it's going to be southeast. And I need that angle theta. I've got two angles here. Theta is the angle I want because theta is the angle between the south line and that line that connects the two ships. That's the angle I want. I can't get that angle right now. Alpha is the angle inside the right triangle. And you know what? I've got two legs here. And if that's a right triangle, I can find any acute angle given that I have the two, if I have two of the three sides. We actually have all three sides, but I don't want to use x because I calculated that. And I'd rather use the 105 and the 63. So here's the next interesting thing. These are two parallel lines cut by a transversal. This is the other red line I've got in here. If it's 78 degrees from north to red line, then it's 78 degrees from south all the way over here to the red line. So alpha and theta have to add up to 78 degrees because two parallel lines cut by a transversal are congruent at their alt-interior angles. There we go. Well, we can calculate alpha using tangent. We can subtract that from 78 and we can come up with theta. That's my plan, is to subtract alpha from 78 degrees. Well, if I have two legs, I'll use tangent. So notice I use tangent of alpha is opposite over adjacent. I do the inverse tangent. Whenever you're looking for an angle, you'll do an inverse function. In this case, it's tangent. And I get alpha to be 31 degrees. So all the way from the south line to that line to the first ship is 78 degrees. I only want the piece on the outside. The piece on the inside is 31. So I take 31 away from 78 and I get 47 degrees. Theta must be 47 because alpha is 31 and their combined total is 78 degrees. So I did it. My bearing is south 47 degrees to the east. So notice what we did here. We found an alt-interior angle. We did an inverse tangent function. We set up a tangent and then we did inverse tangent. And then we subtracted in order to find our answer. I'll tell you that's the way it's always going to be. Alt-interior, tangent, followed by inverse tangent. And you'll either do addition or subtraction depending on the problem. So you might want to review this one again just to see all the different steps we have, or when you go to do the homework you can review this again as well. Alright, let's move on to air navigation. Directions and bearings are specified by measuring from the north and you go clockwise, and that's odd because that will represent positive angles and we're used to clockwise being negative angles. All of our angles, this is airliners now, these are airline pilots or airplane pilots here. They only talk about compass headings, due north being 0, and then they open up and they can give us anything between 0 and 360 degrees. We don't talk about northeast or northwest. We just say 30 degrees, or we say 120 degrees, or we say 270 degrees. So we're going to give you an answer somewhere between 0 and 360. So if I want the direction of this vector here heading toward point B, I would simply say 30 degrees, because that's all it is. You don't say north 30 east, you just say 30 degrees. If I want the direction all the way down here to C, notice that you have to go 180 to go to due south, then you add on the 45 degrees. So the direction of point C here is 225 degrees. And everyone understands that. And I have the direction here to point B as being 30 degrees. So let's get an example out of the way. An airplane flying at 300 miles per hour flies in the direction of 100 degrees for 2 hours. Then it flies in the direction of 190 degrees for an hour and a half. Find the distance from the start point to the plane after the 3.5 hour flight. So here's the first leg. We went 100 degrees, and that means you open to the right 100 degrees, and we ended up right here. Now we're going to have to open up 190 degrees. And there we go. We open up 190 degrees. And so after 3.5 hours in flight, we're sitting down here. The first leg was 1 hour, or excuse me, 2 hours, and the second leg was 1.5 hours. But notice the angles open to the right from the north. To the right from the north. It is 180 degrees to due south, so this little angle in here is probably, what, 10 degrees? Okay. Now remember, I know this angle right here. These are two parallel lines cut by a transversal, so this angle would have to be 80 degrees. The angle right here between the north line going backwards to the first line, or to our first flight path. Because two parallel lines cut by a transversal, same side interior angles, are supplementary. So we're down here, and we want to get home. And we need to find that distance right there. So I draw a new north line right through there, north-south line, and I only mark north. And I want to get the distance, find the distance of the start point. Well, you know what, folks? It's right triangle trigonometry time. So that's going to be a right angle right there at the bend. But let's explain why. I already touched on it a little bit. I said that these are same side interior angles, so this had to be 80 degrees. The angle down here had to be 10 degrees, 190 minus 80. So that was 10. 80 plus 10 is 90. From due north to due south is 180. So if I take those away from 180, I end up with 90 degrees. And so that's a right angle right there at the bend, and the bend will always be the right angle. Now let's go ahead and get distance equals rate times time. So let's find the length here. So it's 300 miles an hour times 2 hours is 600 miles. 300 miles an hour times an hour and a half is 450 miles. So I've got my length of my two legs. We've identified it as a right triangle, so we use Pythagorean theorem to find x. 600 squared plus 450 squared works out to, by the time you add them up and take the square root, 750 miles. So find the distance from point A, or from the start point to where the plane ends up after 3.5 hours, 750. And I'll tell you that that's always going to be a Pythagorean theorem problem, and these problems will always be right triangles, so it'll always be a squared plus b squared equals c squared. So even if you're really bad at drawing, you should be able to get part A done. Here's the hassle. In what direction does the plane need to fly to get back to the start point? And again, it's in airliner talk, so I need the angle. I'm down here where we're at. I need the angle all the way around. I know it's going to be bigger than 180. It's going to be less than 360. In fact, I know it's just going to be this little piece here missing from 360. Had it gone all the way around, it would have been 360. We're missing this little piece. If I could find that little piece, I could subtract it from 360 and we'd be done. Here's a warning. Don't be looking for 270. I know it's there somewhere. You'll never find it. And students try to get above and below 270 because they think they have the perfect drawing. Odds are you're freehanding this like I am. You can't trust yourself. I know it's bigger than 180. I know it's less than 360. That's all I know. So this is the angle we're looking for. We're stretching all the way around. And like I talked about before, if I went all the way around, it'd be 360. I'm only missing this little piece out of 360. So that's my goal, is to find that. I'm going to have to find this whole acute angle from the right triangle first. I'm going to need to find this angle using alt interior angles of two parallel lines cut by a transversal, and then I'll have to do some math. Alright, so alpha represents the entire acute angle. This 10-degree angle is alt interior with that 10-degree angle. Again, two parallel lines cut by a transversal. So this 10-degree angle and this 10-degree angle had to be congruent to each other. I'm going to use tangent to find alpha. And then I'm going to take alpha minus 10 degrees to find the piece that I'm missing here, because these two together have to add up to alpha. And so tangent of alpha is opposite 600 over adjacent 450. Inverse tangent of 1.3 repeating is 53 degrees. So alpha is 53, the whole alpha is 53. This piece is 10 degrees. Well, that only leaves me with 43 degrees. So this piece is 43. If I went all the way around, it'd be 360. I'm missing 43 degrees. So I take 360 minus 43 degrees, and it looks like I'm going to say 317 degrees. So 317. I know. You may want to go back through that one again. But I'll tell you what did we do? We did an alt interior angle, we did a tangent function followed by inverse tangent, and then we did some subtraction. And you'll either add or subtract depending on the problem. Part C is actually not harder. Part B is the hardest part. Part C says how long will it take for the plane to reach its start point. Well, you know the miles. It's 750 miles. And you know it's 300 miles per hour. So if distance equals rate times time, so I put 750, the distance is equal to 300t. T must be equal to distance divided by rate. And so that's all you have to do on that. So that tells you how long it's going to take for the plane to reach start point. So parts A and C aren't too tough. It's that part B that's a hassle. But I'll tell you what, it's always going to be an alt interior angle, a tangent function, right? And you'll use the inverse tangent right after that. And it's either addition or subtraction depending on the problem. But you got to draw it out right first. And the bearing questions use northeast, southwest, those type. That's the ship problems. The airplane problems use compass headings. Angles that start from the north, they open up to the right clockwise, and they can give you any angle between 0 and 360. We don't have north, east, south, or west in that one, just angles between 0 and 360. And you got to play around with this. Hey, that's it for lesson 14. Get to work.